So good morning. Sorry about the short delay. We've been trying to submit a proposal this morning. The deadline was at 10 and we've managed to do it. I'm glad to be here. I don't know if it's just 4 of you. Musa, Victor, Ella. Are there 2 Victors or this is the same Victor?
There are 2.
Okay. So is this the class? No one else is interested in doing. I see Felix as well is coming in. Okay, maybe a few people will join. I don't mind having a small class, obviously, but I thought that there would be a bit more interest. Now, I'm not very prepared, I must confess. Not that I'm not prepared to teach, but usually, you know, introduction and telling you the objectives of the course, what we'll cover, I'm not so prepared because of the proposal I've been working on. I will have to take you back maybe in the next lecture and we go through those. But for today, I wanted to go straight into teaching. Obviously, this is a course on wireless technologies. Wireless is really big. I don't need to give you all the details to become a wireless engineer. As computer engineers, you just need to know how the wireless network works and what are some of the technologies that you need or that you can use. So if you're a wireless engineer, if you are a computer engineer, you may be working on some embedded systems thing and you want to transmit data across the wireless channel. You need to be able to make decisions on what type of wireless connectivity you want to use. You want to know why you're choosing that one. You know, so there are certain scenarios that throw around or throw different technologies in or out of the scenario. Maybe it's a long distance, maybe it's a short distance, maybe low power, stuff like that. So I will be focusing on teaching you wireless technologies from that perspective to allow you to make certain decisions when you get into situations where you need to use wireless technology. I will certainly not focus too much on teaching you how to plan. In the past, I've done that, but then in thinking deep about it, it doesn't seem to me to be a good use of your time to be able to plan a cellular network. You're probably never going to become a cellular planning engineer, but you may be doing some network and you want to transmit your signal over GSM or over LTE or satellite or these other low cost, long distance, low power, so-called low power wide area networks. So we will try to focus on those, on giving you the knowledge that you need to understand wireless technologies and also how you can make decisions which one to use in different scenarios. Now, today I want to start with satellite. I want to start, and I'm going to take off my video and share my screen. Now, this is a link. This link is a link that we can continue to use. It is an open link. As you can see, you can come in before I can come in. Sorry, is there? Let me give you the details of that. I don't know, because if you just click on the link, you can actually join. So let me see. Let me give you the meeting. I don't know how it works, but if the link that I gave is clickable, so you just click and join. But let me give you the details. Yeah, so this is a link that we can continue to use for our classes. It is open. You can use it, but you can use it anytime. You can come in before me, but please don't try to join in when it's not a class time. Some people join at midnight and you're wondering what's happening. So because when you join in, I get emails and I don't want to get useless emails. So let's use it only when it is time for class. I've shared the meeting ID, and for the interest of everybody, I'll share it with everyone. That is the meeting ID, and that is the corresponding passcode. Now, I'm going to share my screen. I see we are now up to 8 people, maybe 7 students. That's not bad. Okay. Just hold on. And so, yeah, so today we are going to start with satellite communication. Now, everyone knows satellite. The word satellite is very common. Everyone can say satellite. A lot of people obviously don't know what they mean. But in our case, actually, that's not our interest. We want to know how it works and what sorts of scenarios it would work, okay? I'm going to be sharing with you slides. And usually, if you show good behavior in attending the class, I will also share my recordings, but I don't want to share recordings if students are not going to attend class and just wait for recordings. Let me know if you can see my shared screen.
Yes, we can see it.
Okay, so long range communications, and we are going to start with satellite. Satellites, I usually use a pen to write, but I think it got a problem. Okay, looks like it will work. Right, so let us really start with the basics of satellite. The word satellite actually means anything that is up above the surface of the Earth and is usually rotating around the Earth or on some journey. So satellite is a general term, but when we use it in communications, we mean electronic devices that have been launched into space at some height above the surface of the Earth, and it is like it's like a moon. It's like moving or moving around the Earth in some direction, but it just keeps moving around the Earth. We are going to see that some actually don't seem like moving. It's not apparent that they are moving, but in fact they are moving. So we use satellites for a number of applications in communications. The first one is, of course, communications. So you can use satellites to transmit information from one place to another, usually over long distances. If I'm using, if I launch my satellite above the Earth, I can send my information through the satellite from Uganda to, say, Europe or to the US, depending on how high it is. In that case, or in that scenario, that satellite is like a repeater. It's working like a repeater. In fact, in most cases, satellites work like repeaters. And the idea of a repeater is that you receive a signal and send it further forward. That is really what a repeater in general terms is. So I can send if I want to send my information to Europe, I have a few options. Right now, there are so many ways you can send it, but the easiest one, for instance, would be I send my information to a satellite, and that satellite relays it back to some location in Europe. Very easy. But obviously, the other options are I can use GSM, so I can use an MTN number, and maybe MTN at some point passes its call through the satellite anyway. But other options include fiber, so it can send it to the coast, and there is a fiber link that goes to Europe. Obviously, the satellite would have an advantage over things like fiber, where you have to dig and put fiber cables in the earth and so on and under the water. But those are some of the things that we are going to be talking about. But yes, we use it for communications, and communications here meaning you can send information through a satellite from one place to another. They are used for GPS, the geographical positioning system. is purely based on satellites. We are going to look at it as a major application of satellites later on in this, not in this lecture, but in this set of notes, or topic for that matter. And then it's also mainly used for television, and in fact you can say television and radio. Okay, so television would now work in the same way that communication that we have just talked about also works. You send a TV, you send your information to the satellite rebroadcasts it over a large area. That's how DSTV works. DSTV, maybe their main station is in South Africa. They have these channels and they send them up to the satellite, and the satellite rebroadcasts them all over sub-Saharan Africa, or whichever area they cover, they have a license to operate in. That is why you need a dish, a so-called dish. We are going to be talking about all of these issues, but that dish is the antenna. So you need a satellite antenna, and if you've noticed, they point it up towards the satellites. Usually it's not just one satellite, of course. It's a number of satellites, but you need a dish to receive that signal. This is different from if you have seen DSTV and you have seen GoTV. Now, GoTV is terrestrial. That's why we use these little antennas, the small Yagi, the wire antennas, whereas this one you need a dish that is pointed up to the sky. Now, if you have your dish actually, and this is fixed somewhere on some wall, this dish is more like it is part of the antenna, but it is not the main antenna. The main antenna is usually somewhere placed on the focal point and placed fixed on the dish. The idea is that when the satellite signal comes, it impinges off of this dish and is reflected into that antenna. If you look at the dish, you realize that actually there is a piece of electronics here in the center, and that's where the cable runs into your decoder. So again, we are going to be talking about these issues once more. The other type of long distance communication is called fixed broadband wireless. You have point-to-point communication. Point-to-point is more like transmission. I want to connect Makerere here and Kasubi here. All I need is a straight link. I don't need to do any gymnastics. I get two antennas, I point them at each other. We are going to be discussing what type of antennas, what type of frequencies would you choose, and so on. And other communication, other systems are systems that include long distances. So the smart grid, if you know the smart grid, it's like an electricity network, like a Mugume network. If it is smart, Mugume has a network all across Uganda. So it's a really large network, and the communication in there can be called long distance communication. And there are other methods, there are other types as well. We are going to look at something like WiMAX is long distance, WiMAX technology, and so on. Now, we are going to start with satellite communication. And we have a number of terms that we need to contend with. Let me just add an empty slide and write on it. The first one is called the Earth Station. What is an Earth Station? Usually, so this is the surface of the Earth, and maybe you have a big dish there, and you have your satellite that is in space, and then you have another dish there. So I can send my signal to the satellite, and the satellite can relay it back to that location. Actually, the satellite sends it back across a big chunk of the Earth, but as long as this satellite dish is here, it can receive it. So these stations that are on the Earth's surface are what we call Earth stations. These are antennas plus radio equipment on the Earth's surface, okay? Those are called Earth stations. Obviously, the satellite is suspended in space. It is up there on top of the Earth. That's why we call it a satellite. We are going to talk a bit about the satellite as well, the piece of equipment. But down here, we usually have typically what you would have in any radio receiver. Obviously, this is your transmitter in this context, and this is a receiver. But you can also have a scenario where that's the receiver and that is the transceiver. And we call this, if you're able to transmit and receive, we call it full duplex or half duplex transmission or transmitter. Or a transceiver. In fact, the other word we use is a transceiver. It can transmit and receive. Another term that we need to learn is the uplink and the downlink plus downlink. Okay, downlink. It is a link that is up, so uplink, and a link going down, which is the downlink. Now, it goes, obviously here you can infer that this is the uplink and this is the downlink. The uplink is the link from the transmitter or the Earth station to the satellite, and the downlink is the link from the satellite back to another Earth station. It can be another Earth station or even the same Earth station. But as long as you have a link from the satellite to the Earth station, we call that a downlink. If you have a link from the transmitter to the satellite, we call it uplink. This term is used generally in communication, even cellular communication. If you are on your phone speaking, and your voice is, of course, data, whatever you're doing, the link that connects you upwards to the base station is called the uplink. And when you are receiving, that link that brings whatever you're listening to on your phone, that is called the downlink. So it is essentially the same thing. You have a phone, you have a tower. This is the uplink, that is the downlink. Another term is transponder. Now, the transponder is actually found here in the satellite. This is the most important piece of electronics in the satellite. What it does is that it receives transmission on the uplink. Obviously, if it is here, then it is receiving information from the transmitter that's on the uplink. And then it processes and retransmits the info on the downlink. Okay, so that is your transponder. It is that electronic piece. It is the piece of electronics that actually they convert the uplink signal into the downlink signal. Obviously, there's a lot of processing that is involved there, usually because the satellites can be so far above the ground. By the time the signal reaches the satellite, it's really low power. It has lost a lot of power. And so usually the transponder has to receive it, usually first correct errors, clean it up, reduce noise, and then amplify it to transmit it back to the Earth station. Amplifying means increasing the power. So if you have a power of 2 watts and you use an amplifier, it becomes a power of 4 or 5 or 10 or whatever, depending on the gain of that amplifier. I think, you know, when I say amplifier in terms of playing music and so on, I'm sure you understand what an amplifier is. Let me just say something that at any point in time, if you don't understand anything, or if you are inquisitive about anything, just ask. You can raise your hand using Zoom and you ask and we have a discussion. I don't want to be on this side talking and I don't know what is happening. But if you don't ask, then obviously I just assume that you are following. Right. Now, how do we categorize communication satellites? One is coverage area. We can use the coverage area of a satellite to categorize it. Some have global coverage. Okay, so there's not one satellite that covers the whole Earth, but we have satellites that cover a third of the Earth. So we really can classify those as global satellites. They are trying to maximize the coverage of the Earth as much as possible. And we are going to see that actually the reason why they can't cover more is because the Earth is spherical. So if you're on one side, the other side is simply hidden from you. That is, I think, reasonable. Others, in terms of coverage area, are regional. Okay, so like the DSTV scenario we were talking about is regional, because maybe DSTV only works in sub-Saharan Africa. So you only launch satellites in that same or the satellite in that region. Of course, the region may be covered by one satellite, but usually actually by a number of satellites. You launch what we call a constellation of satellites. And then another case could be national. So you can launch a satellite to only cover Uganda, then that makes it national. Or a region, or just a region. Like for the large countries like the US or Russia or China or these big countries, you can even cover part of a country. So you have a satellite that covers only a section of the country. That would be a national satellite system. Obviously, it goes without saying, and I think you guys, since you are engineers, this should be very easy for you to interpret, that the higher above the surface of the Earth you launch your satellites, the bigger the region that satellite is going to view. Okay, so if I launch my satellite at 10 kilometers above the Earth, I may not even cover the whole Uganda. Maybe I can, I don't know. But if I launch it at 1,000 kilometers, I should be able to cover Uganda, Kenya, Congo, perhaps, I don't know, something like that. Because you just, you know, the Earth is curved. So if you don't launch your satellite so far up above, the signal at some point meets that edge and it becomes tangential to the Earth, and the rest of the part of the Earth is actually hidden from it. So if you want a large coverage, you launch higher. Can we keep launching higher and higher and higher? Probably not, because at some point, going higher may not even increase your coverage area. Okay. The other way we can categorize satellites is based on service type. Some are fixed service, some are broadcast service, some are mobile service. The broadcast service satellites are like those ones which broadcast TV. So if I have the Earth and I have a satellite here and I send my TV signal to it, I want it to cover a large area. So that is broadcast. It's like if DSTV wants to cover the rest of sub-Saharan Africa, it puts a satellite that can send a signal to cover the whole of sub-Saharan Africa in a broadcast way. The idea of broadcast is that you send a signal out there, and if somebody has a gadget with the right receiver, they will just receive the signal. It's how, so like broadcasting includes TVs, it includes FM radios and other radio stations and so on. Now, when Sanyo FM sends its signal, it doesn't know where the radios are. It doesn't know where you are. You can be at Sedat and you listen. You can be in your hostel and you listen. You know, you move to town, you listen. That is broadcast. They just send out a signal to cover the whole area, and whoever is out there can pick it up as long as you have the right receiver. Because you're not going to use an FM radio to receive satellite signal. Obviously, you need a satellite receiver. Mobile satellite service is one that supports mobile, like mobile phones, for instance. You've always heard that these rebels use satellite phones. That's a service. And then the fixed service is where you have an Earth station and a satellite, and you move a signal from one point to another. These two are fixed. These are fixed. This is fixed. Who has been to Mpoma? I hope you have been to Mpoma, because if I say who has been to Mpoma, I can't even know who has. I don't. So if you've been to Mpoma satellites, I think they call it Mpoma Satellite Station. That is on the road between Kalaji and Mukono. You will see these big dishes. Those are what we call a satellite Earth station. That is an Earth station, actually. So it can receive a signal, it can send a signal. Now let's imagine that MTN wants to send information to, maybe I'm here. In fact, let me do for you a small model to enable you to understand better. So let's say you are calling Europe. This is not the only alternative, but let's say you are calling Europe. You are here in Makerere. This is the Makerere site, and it has antennas and so on. So you will make your call to Makerere. Makerere will but the Makerere site will send that to the what we call the MSC. The MSC is the Mobile Service Center. It's like the server. It's like your cloud of the cellular network. Now the cellular network will realize that you're calling a British number, so it will connect. Usually there is like you have to have a gateway. A gateway usually connects one part of a network and another, and this might go to Mpoma and goes on the satellite, and the satellite will transmit it to a UK satellite, to a UK Earth station, and it can go to some base. It will first go to the MSC of the UK network. From there, it will go to the base station, and we will finally reach your user. So for you, this is the uplink. For this guy, this is the downlink. But this is in terms of the cellular network. But in terms of satellite, this is uplink from Mpoma, and this is downlink. Now, if UK was far, it could actually be, it could pass your signal through a number of satellites. So this is Mpoma. You send your signal here, the signal is sent here, the signal is sent here, until maybe that is, even if you can add another one, it doesn't really matter, until you reach UK, and you can send it to the Earth station in UK, and that Earth station will send it to the MSC. Obviously, instead of going to the Mpoma site, from this gateway, you can use fiber. You know, maybe you go to Dar es Salaam or Mombasa, then you get on the fiber through the East African coast, going all the way through the Gulf into Europe. Do you have any question on this? Okay, are you sure? I'm sure you must have a question, but if you don't have a question, let us continue with our work. The other one is, another categorization is based on general usage, which is the commercial. You can be using satellites for commercial purposes, or military, like the US has so many military satellites, or amateur. Amateur is more like for maybe research or experimental research, amateur satellites, and so on. But for commercial, it is satellites that are out there to make money. Can anyone give me an example? I need a few examples of commercial satellite systems that you know about. Okay. Okay. When you come into the meeting, please, you should use your full names, like DK. I don't know DK now. Yeah, SmartLink. Philip, which one is SmartLink? Maybe I don't know if you can explain, but there's SmartLink, probably that is a satellite, an internet type thing. There's Starlink. I think Starlink is which one is this Elon Musk satellite company that is going to supply internet? Probably Starlink, I think. You have DSTV, for instance. DSTV, clearly their usage is commercial. You have other systems like Inmarsat. These ones you may not know about, to be fair. Inmarsat, Iridium, Obcom, and Intelsat, and so on. So yeah, so it's Starlink, Philip. Yes. Okay, great. And of course, I don't want to ask you which ones are military, because clearly you wouldn't know. Now, classification of satellites. So how do we actually launch satellites into orbit? Okay, so I'm going to open another new slide and we talk a bit about satellite orbits. Now, satellite, obviously the orbit is the path through which the satellite is moving with respect to the Earth. Some are circular. Okay, so by circular, it means you have your Earth and you have a satellite moving around it in some direction. This is just to say that the Earth is at the center of the orbit. That is circular. When I explain elliptical, it's like an ellipse, basically. You could have like a satellite here. No, you could have the Earth, and then you have like an ellipse. So that could be an elliptical orbit. Now, clearly, you see when you draw an ellipse, it has two foci, 1 and 1. So you make sure that the Earth, the center of the Earth is somewhere on one of the foci. It means on one side, the satellite comes close to the Earth and then goes farther away from the Earth on the other side. This is called, you may do this for different reasons. Maybe on the other side, you want the satellite to give you a wider coverage. I don't know, but it is also one way of classifying the orbits of the Earth. So these are the two orbits. One is circular, one is elliptical. Now, another way we can classify orbits, we have the equatorial orbit. We have a polar orbit. And we have, I think it is the, inclined orbit, sorry. I'd forgotten the word. Yeah, it is the inclined orbit. Now, what is the equatorial orbit? The equatorial orbit is technically an orbit along the equator. So that is it means that luckily in Uganda, we are lucky the equator passes through our country. So it means that if you go to the equator and look up, you can see that satellite. It doesn't mean that the satellite will be over there all the time because it moves. Some move faster than the Earth, although some are actually stationary. But the point is that its path is right above the equator. That's what we mean. So it is an equatorial orbit. If I have my Earth like that, we know that the equator passes across it. That is the same path. Obviously, it skirts around and comes back, but it keeps going above the equator or around the Earth. For the polar, it is the opposite. We know the polar regions. We have the North Pole and the South Pole. So instead of this one going across the equator, it actually goes in this fashion. North Pole, South Pole, North Pole, South Pole. So in other words, the polar plane or polar orbit, in fact, you can call them planes or orbits, plane in this instance. The polar orbit and the equatorial orbit are perpendicular to each other. Perpendicular meaning they cross each other in a true sense. They have 90 degrees between them. And then the inclined orbits are any other, or inclined planes are any other plane that is not equatorial nor polar. So any other is inclined. Sometimes we have, let's say we have the Earth. Sometimes we can have our satellites moving like this. Okay. And obviously on the other side, we can have another one moving like this. Okay. We can have moving them at different angles. As long as they are neither equatorial nor polar, they are inclined. And then finally, another thing that we can talk about is if you have the surface of the Earth, I'm going to draw it as a 2D. If you have your satellite launched here, We call that low Earth orbit. That's low Earth orbit. If it's launched somewhere here, we call it medium Earth orbit. And if it's launched up, we call it geostationary orbit. There's a reason why we call it geostationary. I'm going to explain later. But this is usually about 1,000 kilometers. This is maybe 20,000. We are going to look at the classifications of these, and this is about something above 30,000 kilometers. Is it 30,000? Yes. Ella.
Someone is asking, how do we view satellites? Do we use a telescope or something else?
It is a good question, I think. So if you want to see a satellite, I wouldn't say use your naked eye because they are quite far. So a small communication satellites are the size of a fridge. They are quite small. Maybe if it is too big, it is the size of a small car. So you can't easily see them from here without a telescope. But if you had a telescope and you knew where to point, you can see it. The other thing is that the satellites that are closest to Earth actually pass above us in a very short way. It is available to you. It comes on the horizon and will go over the other horizon in a period of about 20 to 30 minutes. So if you don't target it in that time, you have missed it. But luckily, because of you need constant coverage, usually when one is going over the horizon, there is another one that is coming over the horizon. I don't think there is a clear need to view the satellite, but if you had a telescope, you would see it. I'm not very sure that you can see it using your naked eye. Maybe in the night, if it's very dark and the light on the satellite might survive and you see it moving. But again, you need to know where to look. Okay, in the night sky. Okay. Okay. Right. So let us look at this model. I'm going to talk a bit about a few things using this model. Just one moment. All right, sorry about that. Yeah, let's see, how does a satellite able move through one path around the Earth, yet it has a size that can easily be blown by wind? Well, Mwesezi, luckily, there is no wind up there. The wind is in the atmosphere. When we are talking about those distances above the Earth, there is no wind there. It is blank. It is space, essentially. Wind, the edge of space is around 100 kilometers, I think. Yeah, and we are talking about 2,000, 10,000, 5,000, 30,000 kilometers above the Earth. There is no wind there. But secondly, we need to, obviously, it doesn't perfectly remain in its orbit. We do some corrective measures to keep it on. They do corrective measures to keep satellites on track because they can easily steer away from their path. So you just keep, there are forces up there, gravitational forces from other bodies in the space, and so you try to keep correcting the path. But wind is not one of them. There is no wind up there. So anyway, we have what we call the elevation angle. You see, if I'm standing on the Earth, if you're standing on the surface of the Earth, this is your, this is Earth and you're standing here. Maybe the satellite is up here. We know that the Earth is curved, so you draw a tangent. I don't know if you know your math very well. A tangent is not a curve, it is a line right through where you're standing, and you're looking at the satellite like that. This angle theta is called the angle of elevation. Okay, it has a number of a bit of an impact, and I'm going to ask you which ones. Now, if I was standing right above, right below the satellite, my angle of elevation clearly would be 90 degrees. But that is the maximum. The angle of elevation is maximized at 90 degrees. If this one goes over, then my angle of elevation is now being measured. If now I'm here and the satellite is here, my angle of elevation actually has moved to that side. That is my new angle of elevation. So I'm going to ask you a question, okay? But before I ask you a question, let me just demonstrate a few things. Let's say we have the Earth. We have a satellite that is at that point and a satellite that is at that point. That is actually satellite B. That is satellite A. If I'm standing here and this is my tangent, then my angle of elevation to A is that, and my angle of elevation to B is that. Okay. Obviously, we know that satellite B will have higher coverage because it is much higher above the Earth. It can see a wider part of the Earth. Oh, by the way, theta A, I can call this theta A, and this big one, theta B. Now, it goes without saying clearly that theta B is greater than theta A. The angle towards B is clearly greater than the angle towards A. So if you have, what it basically means is that when you are standing at a certain point, as long as these two satellites are aligned vertically, then you'll have a wider angle if the satellite is higher in altitude. Let me give you another example, another point. If I'm here, let's say this is the horizon. By horizon, I mean that is like the last coverage point. You know when you are seeing the sun and the sun is setting, it means that from that point where you're standing, that is your horizon. The sun is going over the horizon. Obviously, if you moved forward, then the sun wouldn't set so fast on you. You know how it works. So if my satellite is at that elevation angle, That actually, let's say my satellite is here. Elevation angle in this case is 0 degrees, not centigrade, 0 degrees. And if my elevation angle is at that point, maybe my satellite is here, and this is a different case because this is not the horizon, right? But here we are at the horizon. That means we are looking at the size of coverage. These two satellites have the same orbit and same height above or altitude above the Earth. This is θ1 and the big one is θ2. Which of these satellites do you think has bigger coverage? The one with angle θ1 or θ2? If they are on the same altitude. This is a different case because these two are not on the same altitude. This case. These are not the same altitude, but if these are on the same altitude, one has, and you are at their horizon, and one has θ2, another one has θ1. Which one would have a wider coverage over the whole Earth? Philip. Philip, you raised the hand, but we can't hear you. If you are having challenges, you can also type your answer. They actually don't have the same coverage. Let me try to elaborate some more. θ2, yes, θ2 would have wider coverage. It's like you have this. So if this is my horizon and I'm looking at that satellite at this point, and this is my horizon and I'm looking at this satellite at that point, you know, it means the next horizon of this satellite is somewhere there. So this one is its coverage, whereas the horizon of this satellite is actually, because you know, it's almost symmetrical. The coverage is almost symmetrical on either side. So this one would have a much wider coverage. Therefore, it goes without saying that the smaller the angle of elevation theta, the wider the coverage. This is also another way of looking at how we expand coverage. But obviously, the easy way is to expand coverage by increasing the height of the satellite at which we launch our satellite. Now, why? Then that means that if the smaller the theta, the better. Then ideally, theta is what? Is 0 degrees. That means that if you're standing here, I'm in my office right now and my horizon is probably Kasubi here. It means that now I'm looking across the hill and that satellite is the best for me because theta is 0. The problem is that theta should not be 0. Theta should actually be greater than 0. Standard-wise, certainly FCC is the Federal Communications Commission, like the UCC of the US. They say that theta should be between 5 degrees and 20 degrees. That means you should not make theta to be 0. The reason is that you shouldn't try to maximize coverage to the extent that your theta is 0. Because you see, if you have the Earth's surface like this, and this is your horizon, there is that part where now your line of the signal is right on the surface of the Earth. For some distance, your line is that line of angle of elevation at 0 degrees is tangential. It is like grazing the surface of the Earth. And we know barriers on the surface of the Earth will affect your signal. Barriers on Earth's surface will affect the Earth. So by lifting it a little bit, you go over those barriers, trees, houses, forests, and so on. And remember, the satellite signal is already small, having moved a long distance. Signal already quite low, having moved a bit of a long distance. Secondly, noise. There is electrical noise from the Earth's surface. So obviously Earth is always generating what we call electrical noise, and this includes heat and so on. These things affect the Earth's surface. Sorry, these things affect the signal coming in, because if you have noise, it will add itself to the noise, and it will make it difficult for you to decode the satellite signal. And thirdly, there is atmospheric attenuation. Now, this is the atmosphere. We've been talking about the atmosphere. The atmosphere is where you have clouds, gases, dust, all those things. Now, if my angle of elevation is at 0 degrees, maybe this is my satellite. If I follow this same orbit, and instead I put my satellite here, instead of there, you can see that this distance, D1, and that distance, D2. Clearly, D2 is greater than D1. What is D2 and D1? These are the distances that your satellite signal traverses through the atmosphere. Okay, so if my angle of elevation is higher, my satellite signal is going to traverse through or to propagate through the atmosphere over a shorter distance than if my elevation angle is low. What does that mean? Atmospheric attenuation is real. Oxygen particles, dust particles, other gases, nitrogen, and so on. All these affect or attenuate the signal. By attenuating, I mean they reduce the power of the signal. So it is advantageous that you spend a shorter time in the atmosphere. For instance, if you are on the downlink, the power is already quite low, and the satellite being a small system, which doesn't have access to the mains power, it uses solar or some other, usually solar to be fair. It doesn't have a lot of power to pump towards the Earth station. So already the transmitted power here is already small. And then you don't want it to contend with a large distance in the atmosphere, because the atmosphere then would have a big chance of completely annihilating or completely attenuating that signal. Okay, so that is another advantage, that if we have an elevation angle that is above 0, it means that our signal spends a shorter distance traversing the atmosphere, and that is an advantage in the sense that it reduces attenuation due to atmospheric effects or atmospheric absorption. Any questions? Let me see in the chat. Okay, maybe. Yeah, in the previous example, it would be θ1, but in the second example, it is θ2. But it is θ1, in the other case, it is the other angle, because obviously they are not at the same altitude. If we are at the same altitude, one with a shorter elevation angle is clearly having a wider coverage. Ella?
Yes, I'm requesting for a repetition of the atmospheric attenuation bit, that diagram. You are a bit very fast.
Okay, I'll do that. Okay, so I have to draw the Earth again. This is the Earth, and this is the atmosphere. I don't know if you know the troposphere, ionosphere, and I think there's another layer between the troposphere and the ionosphere, maybe stratosphere. So there are these layers of the Earth where you have these different gases. In the ionosphere is where you have that ionized gases. You have the ionized gases, and beyond the ionosphere, you go into space. So you go into that emptiness, and it is in that space where we launch our satellites. So where they are fine. No dust, no wind, they can just stay there forever. But this atmosphere has rain, it has gas. Gas include oxygen. Oxygen is particularly bad. It has dust and whatnot. And then the rain, it has clouds. So clouds may be rain or not. And we know that rain, especially water absorbs energy. It absorbs radio waves significantly. So you don't want to contend with what. That's why when you are watching DSTV or Go TV and it starts raining, your picture starts becoming poor, it is because it is the rain. It is just attenuating the signal, or in most cases absorbing and scattering it, so that your antenna is no longer getting enough signal, which is why your pictures start to drop. So my point was that if this was if I'm here and I'm looking at angle of elevation of 0, that is, maybe my satellite is at that point. My signal has to traverse the atmosphere for that long. That is D2. But if on the same orbit, obviously, because we have to compare things on the same orbit, if my angle of elevation was small and I was here, no, my angle of elevation is higher, because here angle of elevation is 0. That is 0. If it is higher, maybe a certain angle, maybe theta is 10 degrees, you can see that actually my signal goes through the atmosphere for only a distance, in this case D1. Clearly D2 is much greater than D1. Now, the longer that your signal spends in the atmosphere, the more it gets attenuated, because there are things that are attenuating it. It is meeting more rain, more gases, more dust particles, more clouds. And the shorter it spends in that area, obviously also the less that it will be attenuated. So we were saying that if you have a higher angle of elevation, your signal traverses the atmosphere for a shorter distance, meaning that it is attenuated less. It is not as attenuated, or it doesn't lose as much power as a signal that spent a longer distance propagating through the atmosphere. I hope that's clearer.
Yes.
Yeah, great. Okay. Yeah, so if we come back here, you can see that not in practice. Ideally, the minimum angle of elevation is 0, but not in practice, where it's usually 5 to 20. Actually, this is an FCC recommendation. Now, the other one is on the coverage angle. The coverage angle is the measure of the portion of the Earth's surface that is visible to the satellite. The portion of the Earth's surface that is visible to the satellite. So remember, the Earth is spherical. So when we are doing this, obviously here it's 2D, but you should visualize it in a 3D sense. Now, if I have my Earth like that, and I have my satellite at that point, it means that at this point it can see, maybe if that is the horizon, and that is the horizon. Now I can draw, it will make like a sort of circle. If you're looking from above, it is like a circle, and it will cover this area on this side of the Earth, and another part similar to this on the other side of the Earth, because the Earth is spherical. So it is seeing a certain area of that Earth, and we call that coverage area, or the coverage angle. In fact, the coverage angle is beta. Okay, beta is the coverage angle. It means that if you have your Earth, and this is your horizon, and that is your horizon, maybe that's your satellite. Obviously, the satellite can be in the center here, and that maybe is the point in the middle of the Earth. That is the center of the Earth in the core. If this is my coverage, then you draw this, then you have your angle beta here as your coverage, as your coverage angle. So in fact, you could redefine that using twice of beta on one side and on the other side. But actually, you need to visualize this as more of a 3D. So that beta is not in 2D form. It's more like a cone. Okay. If you remember what a cone looks like, this is like a cone, but it is actually circular in that sense. That's called coverage angle. And then we have looked at these ones. If you have any questions, now is a good time. But we can continue in the meantime. In our other lectures, I'll be giving you breaks somewhere in the middle. But for today, I will not, because I don't want to teach the whole 2 hours. I'm going to teach maybe another 10 or 15 minutes, and then we stop there. So let's just continue. But if I'm teaching 2 hours, I'll be giving you a break somewhere. So let us look at this one, this diagram. It gives us significant information actually. But before let me see if I can find a table. No, I can't find a table, so that's unfortunate. But let's come back here. Just one moment, because I wanted to give you some values that should help you to visualize this one better. Yes. So I don't know why I don't have this diagram in here. I'm going to add it. Just bear with me. Okay. Bear with me a moment. I just want to show you something before we go through the diagram. And this is 5:30. Okay. Paint. Okay, so I'm going to create a new slide somewhere here. And then I'll put this information. This table is in the book. I'll be giving you a book, but also it should be here. I don't know how I forgot to put it. Okay, so I think you can see my table. We have orbits. And we know the orbits are either low Earth orbit, medium Earth orbit, or geostationary orbit. Now, the orbital period, that is the period that the satellite rotates around the Earth, is 1.5 to 2 hours. This one is 5 to 10 hours, and that one is actually 24 hours, strictly. So that means that for geostationary orbits, all of them have the same orbital height or altitude, because their time is 24 hours, all of them. Whereas you can see these ones have different hours, meaning they have their differences in altitude. You can put it, okay, like altitude range. You can put your low Earth orbit satellite at 500 or up to somewhere 1,500 kilometers, or even sometimes 2,000 or beyond. For medium Earth orbit, we start at 8,000 kilometers to about 18,000 kilometers, or even up to 20,000 kilometers. And this one is always at 35,000 kilometers, 35,863 kilometers. I've actually seen a figure of 35,870 kilometers used. So it depends on the reference of the Earth's surface, maybe sea level, so to speak. Anyway, so the reason why these ones move faster, this is now physics, is that because they are closer to the Earth, you know, when you launch something, how do you ensure that it stays in orbit? It means that the force forcing it forward is equal to the gravitational, is equal to the gravitational pull. Otherwise, the gravity of the Earth would simply pull it back down. So you have got to balance those powers. If you are interested in these things, you can go on YouTube and watch a few videos from NASA or these enthusiasts who describe how you launch things into space. Sometimes I go there and watch, you know, I like to learn those things. So you have got to balance those those powers. Now, when you, like for instance, you can learn about how a rocket gets into orbit when it is going to the International Space Station. How does it get into orbit? How does it align itself with the International Space Station? Those things. It is speed, it is power, it is force. Now, when you want something that is close to the Earth will be facing more gravitational pull by the Earth, that means it needs to move faster for it to actually stay in orbit. That's why they actually move around the Earth faster, but also obviously their orbit is shorter. If you have the Earth, this orbit is clearly shorter than a wider orbit. Secondly, these ones are at a higher altitude, so their times are a bit longer to circle the Earth. That means by this orbital period, it means if you're here and you are seeing the satellite, how long do you wait before you see it again? That is about, for the medium Earth orbit, around 5 to 10 hours. For the geostationary satellite, always 24 hours. What does this mean? It actually means that the geostationary satellite is always has the same speed as the Earth. It moves at the same speed as the Earth. So in other words, its days like 24 hours. You know how we count days? You know, how you spin, and at say 7 a.m., the next 7 a.m. you are back in the same position with respect or with reference to the sun. So that is how you know, okay, I've spent 24 hours. Now the medium Earth orbit moves at that same rate. So if you look at the geostationary satellite, let's say we are lucky and it is above Makerere University. Of course, it wouldn't be above Makerere University. You would have to go to the equator. The geostationary satellite uses an equatorial orbit. They go around the equator. If you stand at the equator, say on that road where there is that thing where you people take pictures, and you look up, if you are lucky and the satellite, geostationary satellite is above you, it means that all the time, every time you come to that place and look up, that same geostationary satellite will still be there. Yes, it is moving. It is just moving at the same pace as the Earth. Now, it is apparent, apparently it's like it's not moving, but of course it is moving. Now, when you are on the surface of the Earth, you can't know that the Earth is actually spinning, yet it is. So it is the same concept. So by giving it 24-hour orbital period, it makes sure that actually once it is suspended above a certain point in space, or at a certain point above Earth, it will always be there, and you get that apparent idea that perhaps this satellite is not moving. Okay. Visibility period. If you are lucky and you can view it as our friend was asking earlier, and you have your satellite, your telescope. If you look on the horizon and you know where to look, a low Earth orbit will pass by you in about 15 to 20 minutes. It will come from the other horizon and pass over you in 15 to 20 minutes. That is what they mean, pass. But obviously another one might be coming over the other horizon again. So you just keep viewing them going over. It's because they are moving much faster. And if you want to cross, go around the whole Earth in 2 hours, yeah, you have to really be moving very fast. For the medium Earth orbit, it is 2 to 8 hours. And for the geostationary orbit, it is permanent in the sense that it remains suspended above the same point because it has the same orbital period. Somebody should look up for me the height of the International Space Station. What is the orbital altitude of the International Space Station? Because actually it is also more of low Earth. It is low Earth, not MOV. It is low Earth. And so if you're lucky to see the International Space Station, if you have a telescope, you can, but if also you're lucky and it's passing above you, you can. It is quite near. The International Space Station is also going to move over the horizon in a very short time. Let me see. Derek, no, they don't. Do they not burn due to the atmosphere or sorry, due to the sun? I mean, these are just 30,000 kilometers above the Earth. That is much smaller than the rest of the distance to the sun. You would say that the sun heat, the heat from the sun that they experience is not so much different from what we would experience. But for us on Earth, there are some gases that we do not experience, obviously. Things like things which are removed by the ozone layer, like those X-rays, gamma rays, they don't reach us. But because the satellite is a metal, it is not affected by these gases. But no, it is not that at 30,000 kilometers, the heat would be much higher than we face here, not at all. The distances to the sun is so big that 30,000 kilometers, I'm sure, is not even 1%, probably not even 0.1%. You can go and read about those figures. So yes, thank you, Musa. So the International Space Station is at 408 kilometers above the Earth. That means it is a low Earth orbit satellite, but it is a much bigger satellite. It is a huge thing. So because it is big, it is possible to see it. And usually when it is passing over a certain country, people know and they can look up. But the point is that it is moving so fast that it will pass over the horizon in around 15 to 20 minutes, and you can miss it. You need to know when it is coming. You can see 28,000 kilometers per hour. That's really fast. But because maybe from one horizon to the other you may be able, as a person standing on the Earth's surface, you might be able to see 500 kilometers from one horizon to the other. If you do the math, you might find that you have about 15 or less. 5,000 kilometers perhaps you can see across the horizon. The other ones is elevation. They are rapid elevations, high and low angles. The reason is because you are closer to the Earth. Slow variations, high angles, and obviously this one, there is no variation at all. Low angles at high latitudes. I don't know what some of these really mean, but you can ignore them. The round trip time really is in milliseconds for low Earth orbit, because you know the satellite moves, the signal moves at a very fast rate. This is tens of milliseconds, but this is the interesting one. Obviously, it is always constant, about 250 milliseconds. We are going to do the math in a moment. Yes. I think Felix, I think the answer is yes. I mean, we are using the time on Earth to measure what we are describing here. In space, time doesn't change necessarily. Yes, there's that's complicated physics, but generally we are using time of the Earth on the surface. Instantaneous ground coverage. So at a diameter at 10 elevation, 10 degree elevation, diameter is related to the coverage angle beta. So your low Earth orbit satellite can cover a diameter of about 600 kilometers, 6,000, sorry, that's really big. That should cover Uganda very well, easily, including Kenya probably, and most of East Africa. This can cover a continent, and you can see these geostationary satellites cover a third of the Earth. Okay, not quite a third, close to a third of the Earth. And it's because the other part is hidden from them due to the spherical nature of the Earth. If it was exposed, the geostationary satellite is so high that it would be able to cover a much bigger percentage. That means that for us to cover the whole Earth, we need 3 geostationary satellites to cover about 70–80% of the Earth. The other part we can't cover because the geostationary satellite is goes across the equatorial plane, and because of that, the polar planes, the areas around the polar regions are hidden from it, again because of the spherical nature of the Earth. So it would never, even if you put 20 of them, they would never cover 100%, because there are areas on the polar side, South and North Pole, that are hidden from it. But generally, if you position your 3 satellites on the geostationary orbit, like here, and I put my satellite here, I measure 120 degrees, I put another and another 120, and I measure another, I should be covering around 75% of the Earth. Right. Examples of low Earth orbit include these. You have Iridium, Global Star, Teledesic, Skybridge, and Orbcom. These are the common ones for medium Earth orbit. You have Inmarsat and Odyssey. Now, and then you have on the geostationary satellite, you have Intelsat, Intersputnik, which is clearly Russian, and Inmarsat. Inmarsat is British, and Intelsat is American. Obviously, this table is from a book that is probably 10 years old. Let me see, this book is about, this is the first edition, it's 2016. So this is not exhaustive. I mean, now Starlink should be somewhere here. The guys at Amazon also have satellites. They are also going to supply internet. So soon we won't need MTN to buy internet. You just buy internet off Intelsat and you keep using it with the satellites above you. That is will be good, given that MTN network is bad. Now let's look at this, and I think I'll stop here on this diagram. We are looking at three things. On one side, we are looking at the period of the satellite. On this side, we are looking at maximum delay. Like delay is round trip, I think. If I send my satellite signal here, and I want to receive the signal, I send at T0 and at T1, and the satellite just receives and resends. What is that time delay? We have already seen that for geostationary satellites, the time delay is 0.25 of a second, or 250 milliseconds. You can see they are telling you geo altitude about, if this is delay, about 250 milliseconds. This one may be for processing, for the transponder to receive and resend. If we are looking at distance here, this is about 35,863 kilometers. Obviously, this is a log scale, so you have to be careful, but this is the orbital satellite for the geostationary satellite. This is the orbital height for the geostationary satellite. Now, the delay keeps increasing as you go up in orbital height. You can see the delay increases, also the period increases, but obviously also the coverage does increase until you reach this point. There is no satellite that is launched above the geostationary satellite. That is the maximum or the widest orbit that we use for our satellites. But if you're looking at low Earth orbit, maybe about, your low Earth orbit is around here. Actually, 5 times 10 to the power 2 is 500 kilometers. This is 1,000 kilometers. So this is your low Earth orbit. You can see very low delay, very short period. We have seen 1 to 2 hours, and also the coverage is correspondingly low. The coverage is there in the green, and I think you can read it off here. So it will be like 5,000 kilometers coverage radius diameter. Your medium Earth orbit is about 20,000. So you're looking at somewhere here in this region. And then our geostationary satellite there. Okay. This is actually the geostationary orbit, but we are going to start here. You can see if this is your Earth, this is actually to scale. This is to scale, drawn to scale. Obviously, the satellites are not drawn to scale, but the Earth and also the size of the geostationary orbit, the height above the Earth, are drawn to scale. The satellites are not drawn to scale because then you wouldn't see anything. They wouldn't even be dots. They would be much smaller. And so I was saying that if this is the center of the Earth, if I have a satellite here, and a satellite here, and a satellite here, this is 120 degrees, 120 degrees, 120 degrees. And remember, the orbit is equatorial. They are moving along the equator, like right below the sun. Then I would cover about 75% of the Earth. Now, you might say, as there are many satellites, they are not just 3. Obviously, each company launches its own satellites, each military launches its own satellites, each country might launch, if it can launch its own satellites. So the satellites will be many, but if a country or whoever is launching is interested in global coverage, they just need to launch 3. Maybe they can launch another group of 3 for redundancy, but there is no need to launch many, because even if you have many, you cannot cover more. But you can launch many for capacity purposes, for redundancy purposes, and so on. And so these are many satellites, but they don't belong to one entity. And these are not exactly the satellites that are there. Maybe there are many more right now in the geostationary orbit. But geo is a bit of a specialized, it's mainly used by the communication satellites to communicate around the Earth. It is not for everyone. It's a country, one country is not going, maybe if you are America, who owns the world, so to speak. But if you are Uganda, why are you launching a satellite in the geo? Just launch in low Earth orbit, you will still cover more than Uganda. And so most of these satellites you see are mainly low Earth orbit. These you hear Rwanda is launching a satellite, you hear Ethiopia is launching. Usually these are low Earth orbit satellites. The technology to launch medium Earth or even geo is much more complicated, and and also operating it also has its complications. Okay, I won't stop here. We will continue with this discussion next time, but please, you can ask any question if you have any question, please. So our discussion, we had mainly centered around these technologies. Just the way I'm telling you about how satellites work, just to understand. Next time when we are done with satellites, I'll give you a scenario and ask you, can satellite work here? Usually it can, but once I've given you knowledge in like 4 or 5 technologies, then I ask you, which one do you think would be more appropriate for a scenario like this? And then it will be very easy for you to tell me with justification. If you have understood, you can give me. I mean, most of the time you might find 2 or 3 technologies can work. As long as the justification is right, I have no reason to discard your contribution. If more entities have need and launch, could there arise a time when the geo orbit is full and can't take more? No. You see, I don't know how many satellites you would have to launch up there for you to say space is finished. And even in altitude, it is not perfect. It's not like it is right on the dot. Maybe some might be 1 kilometer above, some 1 kilometer below. That distance of 2 kilometers is so much smaller than the orbit size. But what would be, it is a very interesting question, actually. So what would be the circumference? Circumference, I don't know, maybe that's how they write that. And this is your radius, maybe. You get the circumference of this and try to put as many satellites as possible, and you tell me how many you would need for you to run out of space. But in a short, no, it is just beyond human imagination to imagine that a satellite, that the geostationary orbit will one day run out of space. And remember, sometimes when satellites grow old, they don't bring them back to Earth, by the way. They usually just take them off the orbit and send them into space. That is why space is full of man-made things. Not full, really. Space is huge, really. But you have things there as big as a bus, or cars that are hovering in the emptiness of space. They are, and then And so these satellites do not have to exist within the orbit forever and ever. Once they run out of energy or they run out of, they no longer work well, maybe the technology is outdated or they have broken, they send them into space and off they go. Again, collision cannot be because they travel at the same speed, remember, and each one knows, and there's some, there are some regulators that regulate the launch. It's not that everyone is launching however they want. So they'll tell you to launch in this position, for instance. It is not a matter of everyone's, it's like it's like how there are rules on the road, although we still knock each other. But the good thing with the geostationary orbit is that it's so much wider that you can easily be 50 kilometers away from the next satellite, even 100, and it would be okay. Like no one is running out of space to launch their satellite. Okay, good, interesting discussion. I hope that it has been nice for you. You know me, you guys, you are in 4th year, so I've taught you twice, or no, once. I've taught you once. This is the second time I'm teaching you. My interest is for you to learn. These other things of marks and whatever, those ones come later. But I want you to learn, and so you do. If you want to take this course, embrace it. Think with me, ask questions, open your mind, and I know you are trying to finish. You're probably tired, and I really wish you well as you finish, but try and bring in as much information as possible. It will be useful to you. So that's the main objective. Thank you, and see you again next week.